Just adjusting this. All right. Okay. Hi everyone. My name is Ali. In case you don't know me, I'm a PhD student here, and I work with Ursula and Devika. And today I'll be talking about a project we've been working on, which is called Second Generation Planets. But I'll only talk about our science a bit. Most of the rest of the talk will be about EOSs and Phantom, which you might find more useful for you, maybe. So the science we're specifically interested in are pulsar planets. For those of you who don't know, neutron stars, which theorists call pulsars neutron stars, they were essentially intermediate mass stars who underwent a supernova explosion at some point, and now they're just very compact stars that are not really doing much, but they're very dense, and they're observed in the form of pulsars. So by now, we've observed over 4,000 pulsars, and 1 in 10 of those have companions so far, at least observed companions. And there's about, 7 or 8, depending on who you ask, of these companions, which have planetary masses, and these are what we call the pulsar planets. So they've been subjects of, fascination. Like this was from NASA's Halloween set of posters a few years ago, planets around dead stars. And the interesting thing is they were actually the first exoplanets found because pulsars, if there's something around them, they're very easy to detect. So in this table here, you can see the first 3 pulsar planets discovered, and they have all very Earth-sized masses, and their orbital separations are like all within half an AU, so they're quite close to the neutron star. Now, the thing that has been the subject of a lot of, speculation is how these planets came to be. What's the origin of these pulsar planets? There's lots of ideas that Cyril Finney kind of nicely classified into 2 family of scenarios, which I'm borrowing from him in this talk. The first set of scenarios for these planets he named salamander scenarios, based on a mythical creature which apparently likes being in fire and can enjoy it. So these family of scenarios to explain pulsar planets are basically survival scenarios. So planets would have been formed similar to how most of the planets we know around young stars form, and would have survived the very chaotic evolution of these systems. The consensus is that, neutron stars' evolutions are too explosive for planets that close to survive. So most people in the literature don't really consider this. The consensus is on another family of scenarios known as Memnonides, or dubbed as Memnonides, which is based on a Greek myth about a hero dying, and from the ashes of a burning corpse, birds are made. So essentially, the pulsar planets ideas mostly tend to being formed from the ashes or debris or remnants of a somehow disrupted star. So most people agree that these planets are better explained through some sort of Memnonides scenario, but there are a ton of Memnonides scenarios out there. And here I've just divided them into 2 main kind of groups. So in terms of how they're formed. So one group of ideas is that these pulsar planets were formed in second-generation disks. What that means is later on in the evolution of the neutron star, somehow a disk was made which resembled protoplanetary disks, and planets were formed. So one idea is, for example, a supernova event made a fallback disk, and that became a protoplanetary disk. Another family of scenarios is, binarity-induced planet formation. So we know that neutron stars, since they're relatively massive, most of them have companions, and pulsars, since they have very strong winds, if it irradiates a companion for long enough, it just might lose enough mass to reach planet-sized masses. So this is another family of scenarios. But then we've got hybrid scenarios, which both involve a companion and the formation of a second-generation disk somehow. So one of them that has been studied years ago, and a simulation of it exists here, is if the neutron star plunges after its natal kick and into its companion, it might steal some mass that might form a protoplanetary disk. So that's just one idea. But the one I've been working on is what most people have been assuming is what happens, which is the tidal disruption of the companion. So what that means, as you can see in a simulation I have here, is if you have a neutron star and a companion, survive the supernova explosion, if they shrink enough for mass transfers to start, which can happen with, gravitational waves or other mechanisms, mass transfer can start. And if this companion star is degenerate, like white dwarfs, for example, the mass transfer will become very unstable, and the star is eventually tidally destruct because, well, with degenerate stars, you expand when you lose mass, so things get chaotic pretty quickly. So when the star destructs, as you see, a bunch of debris remains. And the science I'm interested in is, would this disrupted material be able to form a disk kind of structure similar to planet-forming disks? And would it explain the observed systems we know? But that's enough about the science we're interested in. From now on, I'm just going to talk about thermodynamics. So when you want to simulate white dwarfs in Phantom or any other hydro code, there is a few complications because white dwarfs are supported by degeneracy pressure of their electrons the closer you go to their core. And the problem with that is there's a whole bunch of different statistical mechanics going into that, because the partition functions, which tells you how much, well, electrons exist in a certain energy in a certain, space, differ from the classical Maxwell-Boltzmann distribution. So from those, you don't really get clean equation of states, equations that you can get for ideal gases in the form of, a function of pressure is a function of density and internal energy. So things get a bit messy. For Fermi-Dirac, you generally don't even get analytical expressions at all. So there's a bit of complication to that. There's two possible ways we can simulate white dwarf equations of states in Phantom. One of them is a rabbit hole. I'll first start with the one that's not, but I'll just tell you what we found along the way, because it might be useful to some of you. All right, the first module, EOS Helmholtz, which was developed by Terence Tricot, is already in Phantom, and it was intended to simulate white dwarfs with. It's based on some tabulated Fermi integrals, so we don't have equation of state equations, we just have tables. And these tables can essentially be used even if you're using ideal gases, because they're supposed to have, ideal gas contributions, radiation, etc. So they're kind of comprehensive. The nice thing about them, which I'm not going to talk about, but you can ask me about later, is they're made in a way that thermodynamic consistency is ensured. Don't ask me what that is now, but you can ask me later. I just wanted to tell you all, if you've been trying to work with it a year ago or so, it had some problems crept in, but we fixed them all. So whoever needs to simulate white dwarfs can go ahead and use this now. The other, this was the rabbit hole. The other thing we thought might work for our systems was EOS Mesa. Now, some of you might have used this already, but essentially EOS Mesa was made by Thomas Reichardt. And what he did was he used the Mesa stellar evolution code, because Mesa stellar evolution code has a bunch of EOS routines that you can give a composition and two independent thermal variables and get the rest out, right? And this is from the Mesa website. It's basically a blend of different EOSs, and it's meant to be very comprehensive. So it has recombination effects, radiation. Even these purple regions are basically the Helmholtz tables I just discussed. So we thought, hey, these have everything. Let's just use these. Thomas made these tables and just tabulated them into Phantom a few years ago. And the units, and gave internal energy and density as thermal variables, so there's no root-solving complications required. There were a few problems with it for our case, though. The first simplest one is the tables right now that exist in Phantom are only for hydrogen-helium rich composition. So if you have a white dwarf which is 99% metals, you just don't have the tables to use them. Another minor issue that arose is Mesa itself updated its EOS modules, and when you take the residuals of what's in Phantom right now, some properties changed quite a bit. So it is worth updating. Okay, almost done. So that kind of, we at some point we wanted to do white dwarfs with these tables, which was a bad idea, but we just reinvented the wheel because the wheel wasn't anywhere. We just made customized wrappers to make EOS tables for any composition, resolution, whatever you want to give. And now it exists and we're not using it. So if anyone has any ideas of or think it might be useful for them, have a chat with me. One idea we had was change the thermal variable from internal energy to entropy to use it in the GR code, because in GR they evolve entropy instead of internal energy. So that's one application me and Fitz are working on. But if there's any other idea you have, let me know. And I'll end kind of on a sad note, but the reason we ended up not using EOS Mesa for white dwarfs is close to the core of a white dwarf. This black line is a profile of Mesa white dwarf. Close to the core, you have zero temperature degeneracy, which means your table kind of lies on the edge of, your white dwarf lies on the edge of physical and non-physical regions. And if your table resolution is a bit not what it should be, or the abundance is a bit different, you get points that are basically in non-physical regimes. And this caused lots of problems because, Phantom's a hydrocode, it doesn't really care, and, stuff started flinging into more non-physical regimes. So takeaway is don't use these for white dwarfs, but you can use these for other stuff, which is very cool. I'm gonna stop there because I might be out of time, but this is my summary slide. Yeah, thank you for listening. Thank you.
Thanks, Ali. Really cool stuff. A bit of a question on the general background science case. So when say you have observations of a planet, just trying to think through it, and you're trying to distinguish between these formation scenarios of like a black widow. So one of the things is formation in the disk. The paper you found with the JWST planet that just completely has a carbon atmosphere. Like there, it's clear that something funky must have been going on, right?
Mm-hmm.
But I'm wondering, like, how do you separate that from, for example, a black widow scenario, or
well, that's the
surviving
good question. So I'm gonna go back to the first slide. Just all right. So this table is probably the a table of the pulsar planet, at least the ones people agree are pulsar planets and not just noise. This system, which has 3 planets, is the most interesting one for our science case, because these planets seem to, like, they're in resonance and they seem to be coplanar and their eccentricities are low. Everything hints that they have had a common origin. But if you look at the rest, so for example, well, forget this one for a second, but these all have a very short period, so they're very close to the neutron star, right? These are all most probably black widows, or essentially, for those of you who don't know, it's just radiation from the neutron star has stripped the companion so much that it's basically a 10 Jupiter mass object. And even the mass regimes are different. So our scenario may not really apply to these, especially if there's not an exoplanet in the system, like there's nothing to speculate on. And the system you mentioned is actually, I think, J2322, which they managed to measure the atmosphere. That actually kind of puts some skepticism as to whether it is a black widow. I still think it is, but because that's the best way to organically explain the orbital parameters. But this system is very weird. There's no nicer way to explain this than the mess I'm trying to simulate.
Just a comment, but on the stripping side, I think there's less extreme analogs with massive stars and stellar companions. So there's some brown dwarf companions found with sphere that seem to not be like binary form. They must have been stripped by the.
Well, I'm not really an expert in black widow, so that's as far as I know.
Yeah, okay. Fair enough.
But it is a gray area, to be fair.
Thank you again.
Thank you.
Kevin.